Welcome to Acid-Base Chemistry Part 4. This tutorial is going to focus on equilibrium and specifically how it relates to acid-base chemistry, and we'll also apply the principles proposed by Le Chatlier. Now, this is a really big and important topic, and this is a pretty long tutorial, so have yourself set up to be ready to focus. Let's get started. Alrighty. Now, equilibrium reactions occur for things beyond acid-base reactions, but for our course, this is the most important application. So when we talk about an equilibrium reaction, we've already seen, I referred to it by the reaction arrows, but now we're going to flesh out what exactly that means, right? So this is where we have a forward reaction. Oops, we'll use green there. And a reverse reaction happening simultaneously. So at equilibrium, the forward and reverse reactions are proceeding at the same rate. Another interesting feature of equilibrium reactions is when a reaction is at a state of equilibrium, the concentration of the reactants and the products no longer change. So let's just take on this first page, let's focus on the definition of equilibrium and make sure that we understand what that means. All right, so the first part of the definition had to do with the reaction rates. So basically what that first statement says is that the rate forward equals the rate of the reverse reaction. All right, so let's study this using acid-base chemistry. So we have a simple acid here, and it's dissociating, but it's not a strong acid, it's a weak acid. So we have the forward reaction causing the dissociation, and then we have the reverse reaction which reforms the acid. So here we have it in words, and remember we'll be using green for the forward reaction, and we'll use red for the reverse reaction. So we've talked about it using English. Now let's do it graphically. So we'll make a graph and we'll put time on the x-axis, and we're going to put the reaction rate on the y-axis. So based off of our earlier studies of reaction chemistry, we know that when we first begin the reaction, we have 100% of the acid. And so it's at a high concentration, so the rate starts very fast, but then as the reaction proceeds, the rate slows down. So this is rate forward. So we have a high concentration of our reactant, so the rate is fast, and then as the reaction proceeds, the rate slows down. Now the reverse reaction, initially there is no H plus or A minus, so there is no reaction rates, and then as the forward reaction proceeds, we start to produce products, and then those products can begin the reverse reaction. And so then we see at this point right here, this is where equilibrium begins. So using our reaction rate definition of equilibrium, once the reaction begins, the forward rate will decrease, the reverse rate will increase, and at the point of equilibrium, the forward rate and the reverse rate are equal. Notice that both reactions are continuing. Nothing has stopped, it's just to the point. So if we look right here on our graph, we would say that this is where rate forward equals rate reverse. And so that signifies equilibrium. Okay, Now let's look at the definition of equilibrium in terms of the concentration of the reactants and products, right? So what we said here was that the concentration of reactants and products will stop changing at equilibrium. So there are two products here, but because we have a 1-to-1-to-1 reaction, I'll just focus on the H plus concentration since we're really focusing on our acid-base chemistry here. Okay, so this graph, it will also have time on the x-axis, and then here we'll be looking at concentrations. So remembering that the square brackets represent concentrations. So we will be looking at the concentration of our reactant, and we'll look at the concentration of the product. And we'll just focus, to keep the graph simple, we'll focus on the H plus concentration since that's related to the acidity. So initially all we have is HA, so the concentration is very high, and so but it will drop, and then at equilibrium it flattens out. So this would be the concentration of HA. Now initially all we have is HA. The forward reaction proceeds and we start to produce H plus. And so the H plus concentration will increase until we've reached equilibrium. And so notice we should be at the same spot, right? So equilibrium begins, or we could say that the system has reached a state of equilibrium. Alrighty, so that would be this time here. So remembering that this red curve is representing the H plus concentration. So equilibrium reactions can create an illusion because we see that the product concentration is remaining stable and the reactant concentration is remaining stable. We might have the illusion that nothing is going on. So we have to understand the concept of reaction rates, that the forward and reverse reaction are still proceeding. However, at equilibrium, because the reaction rates are equal, we observe no change in the concentration of reactants and products. Okay, so what general statement can we make about the concentration of reactants and products at equilibrium? Well, the concentration of reactants, right, equals a constant, right, this value right here, and the that would be the reactants there, and then the concentration of the products is also a constant. But it's important to note, right, that the concentration of reactants and products are not equal, right? Equilibrium is about that that each respective concentration is remaining the same. And then to really emphasize a key point, at equilibrium, have the reaction stopped? No, it's simply that the rate forward equals the rate reverse. Okay, so let's go on to the next page. And just that because this is such an essential aspect of equilibrium, sometimes you'll hear it referred to as dynamic equilibrium. All right? So why is the term dynamic often used to describe equilibrium? If you look in the dictionary, you'll see that dynamic is defined as motion, related to motion or movement. So sometimes when you hear equilibrium described, you'll hear it described as dynamic equilibrium because whoever's speaking really wants to emphasize that the forward and reverse reactions keep going, right? They keep reacting, keep moving. It's because they're equal that we have the illusion that no change is occurring. Okay, equilibrium. Alrighty. So now let's take our understanding of equilibrium and map it out with a reaction energy diagram to bring everything together. Alright? So we have an exothermic reaction. Those are considered spontaneous, right? That tells us the products are more stable than the reactants, right? But a spontaneous reaction does not necessarily equate to fast. So this is what can happen. There we go. So there's our reaction curve. Energy along the y-axis and time along the x-axis. And so we're going to draw a curve that is exothermic. So that tells us the products are lower in energy than the reactants. However, we see that it's not necessarily fast, right? So that tells us, what does that tell us? That tells us we have a large activation energy. And so here would be, there is our thermodynamics. And there is our kinetics. Here is our transition state. Okay, and now if we overlay a curve where we've added a catalyst, we can see that then we would lower the activation energy. Okay. So this reaction energy diagram, this would help us think about equilibrium, in that if we have a reaction where we have A going to B, for example, we would look at this reaction, and so we would say reactant A, products B, because the products are lower in energy, we would say that this reaction, the equilibrium goes to the right. All right? So we could rewrite this showing a larger arrow to the right, and we would say, right, because thermodynamically, the reaction favors products. Right? So with our equilibrium arrows, then we show that as a larger arrow to the right and a smaller arrow to the left. And so these equilibrium arrows are linked with the thermodynamics. Now that we understand what it means for a system to be in equilibrium, let's look at what happens when we disrupt that equilibrium. And this is an important concept as we venture into biochemistry, because our bodies are constantly changing. We're exercising, we're eating, we're sleeping. So our body tries to be at equilibrium, and we're constantly putting stresses or changes in that our body has to respond to. So let's look at changing equilibrium conditions. So we'll build off the concept on the last page, that when we write reactions, we always have the reactants on the left, and then we would have our forward and reverse reactions, and products are on the right. So linguistically, when a reaction is favored to the right, it favors the products, then we say the reaction goes to the right. If we're looking at a reaction that favors the reverse reaction, since the reactants are on the left, we will say that the equilibrium shifts left. So it's really important to be aware of the different ways that people will describe changing equilibrium conditions, but it's all based on your understanding of chemical reactions. So a gentleman by the name of Le Chatlier, he was the one that summarized his observations. He noted that if a stress is applied to a system at equilibrium, the equilibrium shifts to relieve the stress. So it's either going to shift to the right and produce more products, or it's going to shift to the left and produce more reactants. So I think we all feel stress in our lives from time to time, but how does a chemical reaction feel stress? Well, if we change the concentration of reactants, right, or products, that will create stress, right? Think about the definition of an equilibrium. So if we change these concentrations, that creates stress. Or if we change the temperature, that creates stress. And then a concept that we haven't looked at a lot, but we will focus on now, if we have a change in pressure or volume, that will also create stress. We can use a Teeter-Totter method to really help apply these concepts. So before we go into exploring each of these different stresses for chemical systems, I want to show you the strategy I'm going to use. So when a system is at equilibrium, right, we will just consider it like a teeter-totter that's perfectly balanced. All right? So now as we add stress, so there's different ways to add stress, right? We could either increase something on the reactant side, or we could decrease something on the product side. Either way, either one of these stresses is what's it going to do to our teeter-totter, right? It's going to cause our teeter-totter to slide to the right. And so that tells us that we are going to shift our equilibrium to the right. If, on the other hand, our system's at equilibrium, right, we have the option to do the reverse. We could increase something on the product side or decrease something on the reactant side. And so what will that do to our teeter-totter, right? It's going to slide our teeter-totter to the right, or excuse me, to the left. Yeah, so there we go. And so then we would write the arrows this way, and we would say left. All right, so if this is looking a little funky to you, I'll apply it right away to help you make sense out of it. All right, so let's start with looking at concentration changes. All right, so here we have a reaction, phosphorus trichloride with chlorine to produce phosphorus pentoxide with some heat. So we had a system at equilibrium, and then what did we do, right? We added stress. Okay, how did we add the stress? We added the stress by adding, we added chlorine. All right, so what did we do? We increased the chlorine concentration. Okay, so let's use our teeter-totter. So the system was at equilibrium, and then we look at chlorine. Chlorine's on the reactant side, so we put it on the left side of the teeter-totter. What did we do with that chlorine? Right, we increased it. So by pushing up on the teeter-totter, what do? Right, we're going to slide it to the right. So we would say that we have shifted the equilibrium to the right. And remember, right, that on the right side are the products. So this equilibrium is going to favor the formation of products. Now let's look at our data to verify that that's what happened. Alrighty, so here was our original. So once we added the stress, we are here. And so we were at equilibrium, we added stress, so now we have our new conditions, and then we let the system achieve equilibrium. So if we look at the concentration of the phosphorus trichloride, we see it started at 5, and then it decreased to 4.4. So the concentration of the phosphorus trichloride decreased. And that makes sense. We have less reactants now because our equilibrium favors the formation of products. What happened to the chlorine concentration? Well, the original chlorine concentration was 3 plus 7, which is 10. And once we have reached equilibrium, it's only 8.39. And this makes sense because these are both reactants. So because the equilibrium has shifted to the right, we've had a loss of reactants. And now if we look at our product, we started with a value of 5 for our phosphorus pentachloride, and once we've reached equilibrium, we're up to 6.12. So the concentration of our product has increased, which makes sense if the equilibrium is shifting to the right. Right? So just to really re-emphasize, which way did the equilibrium shift? To the right, to favor product formation. Right? So reactants and products. All right, so let's do one more example with concentration before we move on to temperature. So once again, we start with our reaction at equilibrium, and this time we're going to decrease the phosphorus trichloride. So the phosphorus trichloride is a reactant, so we'll put that on the reactant side, and we're decreasing, so we're going to pull down on our teeter-totter there. So that's going to shift the equilibrium, right? Shifts the equilibrium to the left. When the equilibrium is shifted to the left, it's going to favor reactants. Okay, so that covers concentration changes and how those affect equilibrium. Now we'll look at how temperature affects equilibrium. So we'll just go ahead and stay with the same reaction. It works pretty well. And then we'll jump into acid-base chemistry. But to really explore all the aspects of equilibrium, we had to go to an inorganic reaction. All right, so what happens when we change the temperature, right? If we increase the temperature, what happens to the kinetic energy, right? We're going to increase the kinetic energy, and so we can think of that as an increase in heat. So now that we've had a review of the kinetic theory of matter and energy review there, now let's look at our reaction, and we notice heat, right? Heat is a product, right? We would say that heat is released by this reaction when it goes in the forward direction. So, does that mean this reaction is endothermic or exothermic? Definitely exothermic. And if we had to assign a value to the reaction enthalpy, we would put a minus delta H. Now, so this is kind of a rehash of up above, right? So if we're increasing the temperature, right, we're increasing the heat. So let's use our teeter-totter model and look at the reaction we're studying. So here is our reaction, and heat is on the product side. So we put heat over here on the right because that's where it appears. And so if we increase the temperature, we're increasing the heat. So we are going to slide the reaction to the left, and so that favors the reverse reaction. So if we were drawing our equilibrium reaction arrows, we would put a large arrow to the left. Now, what does this do to the equilibrium? I've pretty much already said it, right? It shifts the equilibrium to the left. And so when we shift the equilibrium to the left, that favors reactants. Right? So adding heat is going to push the reaction in the reverse. All right. Now, it's the same reaction, so heat is going to stay on the product side. However, in this next scenario, what happens if we decrease the temperature? If we decrease the temperature, we slide our teeter-totter to the right, and so now it favors the forward reaction. And anytime that we favor the forward reaction, we say we've shifted the equilibrium to the right. And so this is going to favor the formation of products. Okay, and so now to bring this all together, let's do a reaction energy diagram. So our y-axis is energy, our x-axis is time, and we see here it's exothermic, so our products are lower in energy than our reactants. But now we have a specific reaction, so we can write the reactants that are involved and the products. We can include the chemical formulas. The heat that is released as a product is shown here in the curve. And then we have our transition state, and we might as well fill in this. So that would represent, so as we add heat, we have more energy to go in the reverse reaction to favor the reactants. And if we lower the temperature, right, this is a good thing to point out, right? So this is the E sub A for the forward reaction. If we want to look at the reverse reaction, right, if we go in the reverse reaction, we would start here and go up to the transition state. So E sub A for the reverse reaction. So this can help us see that as we add heat, there's more energy to overcome this large activation energy and produce the reactants. At low temperature, there's not as much energy available, and so the forward reaction is favored because it has a much smaller hill. And now we will look at the effects of pressure changes on equilibrium. Okay, so to talk about this, we need a little bit of review. What happens when we change the pressure? So we need to look back at Boyle's law from the gas laws, right? And Boyle's law tells us P1 V1 equals P2 V2. If you don't remember Boyle's law, there is a gas law tutorial, but really we don't have to do calculations here. It's about concepts, right? What Boyle's law tells us is that if we increase the pressure, we're going to decrease the volume, or vice versa. If we decrease the pressure, we will increase the volume. So that's the main concept that we need to bring from earlier chapters to understand the role of pressure and how it changes, impacts equilibrium. Now, in figuring out how to teach this to students, I learned a Bennetism that I would like to teach you. And so we want to look at our reaction whenever we are going to be asked about pressure or volume. So that's one key point, right? That we'll talk about the pressure change, but it could also be volume because they're linked by Boyle's law. So anytime we're asked to do an equilibrium question and we talk about a change in volume or pressure, the first thing we want to do is we want to look at our reactants and see how many moles of gas are present. So we look at the reaction coefficients, 1 plus 1. So we have 2 moles of gas. Okay, and then if we look at the products, we only, right, remembering our coefficients of 1, right? So if we read this, 1 mole of phosphorus trichloride reacts with 1 mole of chlorine to produce 1 mole of product. So using our reaction coefficients. And so then for the products, we only have 1 mole of gas. Okay, so what I figured out was that whichever side of the reaction has more moles of gas, put a P there for pressure. Right? So add P for pressure to the side of the reaction that has more moles of gas. Oops. Okay, now we can use our teeter-totter approach, right? So the system is at equilibrium, and we're going to increase the pressure because there's 2 moles of pressure on the reactant side. We'll put pressure on the left, and it says to increase. So if we increase the pressure, we are going to shift the equilibrium to the right. Right? And that's going to favor products. Alrighty. So you can just, this is all you need. If you want a little more, just think about as we increase the pressure, we decrease the volume. And so that creates stress for the side of the reaction with more moles of gas. You could, I don't know, for me, like experientially, imagine that you're riding by yourself in the elevator with only one other person. It's not stressful at all. There's lots of room for everybody. However, I think we've all ridden in an elevator that was jammed full of people. It can be a little stressful depending on, you know. So that's how the gas molecules feel. So if there are more moles of gas present, increasing the pressure or decreasing the volume creates stress for this side of the reaction, and so it wants to relieve the stress. So it produces the single mole of gas on the product side. Okay, one last example with changing pressure. Look at this next reaction here. Would a change in pressure affect this following reaction? Well, we look here and we see we have 2 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So would a change in pressure affect this reaction? No, right? And then why? Because, right, because we have the same number of moles on each side. Okay, and I wasn't, right, same number of moles of gas. on each side. So if we had an additional reactant or product that was in the liquid or the solid phase, we would not consider those in this scenario. So pressure and volume are going to only create stress in reactions where we have gaseous products and or reactants. Okay, so now we have a concept that wasn't talked about before, but it's important to look at the effects of a catalyst. So, do catalysts change the position of equilibrium? No. What do catalysts change, right? They decrease the activation energy, which increases the reaction rate. So if you think about the equilibrium as the destination, catalysts do not affect the destination, but they do affect how fast we get there. So because the reaction rate is increased, the system reaches equilibrium faster. Okay, so there is an influence, but not on the actual ratio. There's no change in the ratio of reactants to products. It's just how fast we get there, right? And so you guys should be able to do these reaction energy diagrams in your sleep by now. But so we'll just kind of quickly review, right? So it's exothermic. And if we go with or without a catalyst, and then of course the solid is without catalyst. Alrighty, so and then here we have our reactants and products. Okay, so a catalyst does not change the energy difference between the reactants and the products. So it's this energy difference that determines equilibrium. Okay, what the catalyst simply does is without the catalyst, we have a larger activation energy, therefore slower reaction. And with the catalyst, we have a smaller activation energy, so we get a faster reaction. So the actual concentration of reactants and products won't change at equilibrium. It's just how fastly we get there. And so just to come full circle here, then let's think about what happens reaction rates for this reaction above. This is where we started looking at equilibrium. There we go. So here we're back at reaction rates, and then this will be time. Okay, so if we have without a catalyst, it takes quite a bit of time for the forward and reverse reactions. So this is rate forward, no catalyst. And this is rate reverse, no catalyst. And so simply by adding the catalyst, we'll do that one, right? Then the reaction is proceeding much faster. Right? So with no catalyst, equilibrium here. With the catalyst, then we can see that we reach equilibrium sooner. So there is, so we've described it in words, and then there's a graph to help you depending on which style you like to receive your information. Okay, and now to finalize all of this, we want to take your understanding of equilibrium and make sure that you can apply it to some important acid-base reactions. So it's like, I thought this was on acid-base chemistry. It is, but But this is the tricky part. We had to understand what it meant for a system to be in equilibrium and what happens when we disrupt that equilibrium. So now we have all of the information we need to study two important reaction systems inside our body. The bicarbonate equilibrium system, it regulates the concentration of hydrogen ions in our blood. And that is something that is essential to our health. So this is a very important system to understand, and we need to understand it in the concept of dynamic equilibrium. Alrighty, so then if we look here, alright, so here is our carbonic acid, and then these would be the hydrogen ions or the protons in our blood, and the bicarbonate. So these are present in our blood. And then our breath, right? So our breath contains CO2 and water, but we'll just focus on the CO2. This is controlled through our breath. So now we can link this all together. So let's look at the example of hyperventilation, right? So hyper, like someone's hyperactive, too much energy. Hyperventilation, too much breathing. Comes from a variety of sources: anxiety, hysteria, altitude sickness, intense exercise. So there's lots of reasons we could start hyperventilating. This is the key. This is the goal of this section. What would you expect a patient's blood, would you expect a patient's blood carbon dioxide concentration to increase or decrease if we are hyperventilating? Right? So this reaction is occurring in our blood, but it's controlled by the breath. So if we're breathing a lot, right, what's going to happen? The CO2 concentration in our blood is going to decrease. Now, what happens to the hydrogen ion concentration? So we look at our teeter-totter, and so the CO2 and the water are on the left, and the hydrogen ions and the bicarbonate are on the right. So if we're hyperventilating, we're releasing a lot of CO2, so we're decreasing our CO2 concentration. So that is going to slide the equilibrium. It's going to shift it to the left. So the equilibrium shifts to the left. And so what is that going to do, right? So that means it favors the CO2. So what happens to our hydrogen ion concentration? Our hydrogen ion concentration decreases. Alrighty, so and then we will come back to this concept a little later in the tutorial series when we learn a bit more about pH. But for now, we'll just focus on the equilibrium. The phosphate buffer system, oops, got a typo there. So this is important because it regulates the hydrogen ion concentration in our cells. Right? So the bicarbonate and the phosphate buffer systems are two very important buffer systems, and there's a future tutorial that will talk about buffer systems, but the main thing is that they're related to controlling the hydrogen ion concentration. So that's all we need to know for now. Alrighty. Now, the dihydrogen phosphate, it passes from the body in our urine. diuretics are a substance that will cause frequent urination. All right? So what happens to the hydrogen ion concentration when a person takes diuretics? So it increases the urination, and so then that increases the loss of the biphosphate, or the dihydrogen phosphate. So basically, so what does this say? So if we're increasing the loss, that means we're decreasing our dihydrogen phosphate concentration. All right, so now that we've reasoned that through, we'll go to our Teeter-Totter method. The dihydrogen phosphate is on the left, and it's going to decrease if we're peeing a lot, we're letting go, so we're decreasing this concentration. So it shifts our equilibrium to the left. So equilibrium shifts left. And so what does that do to our hydrogen ion concentration? It decreases our hydrogen ion concentration. Alrighty, okay, that was a lot of information, but it's very important, and because it's really a mastery topic. You see how thermodynamics and kinetics and the different reaction conditions all come into play, and it's a very important concept in understanding the health inside of us. So please take some time now to reinforce your understanding by practicing some homework questions.